malware is looking for. What that caused basically is that Firefox was unable to execute its garbage collector and other memory-related feature to balance it. So over time, the process in its behavior might give us away on the victim computer. So we had to redesign Jinx. We had to make Jinx more sophisticated. Basically, we made Jinx to be completely distributed within itself. Instead of being executed at once, we're now being executed on a different time slices. For that, we had to accomplish a scheduler within Jinx that can schedule time slices. The function setInterval, a very standard JavaScript feature, working very similar to the signal function in Linux, allow us to basically fake an interrupt scheduled to JavaScript itself every X seconds. That way, we can establish a very primitive yet efficient scheduler to call ourselves. But each task had to find a way to preserve or keep track of the different states it's going through. So we decided to abuse the feature of anchors, aka hashes. Hashes allow the website to append information to the URL itself, all that without reloading the page. So here you can see an example of the scheduler. You have a very simple primitive scheduler going into the function. We are clearing any previous interval requests to avoid any race condition. Right afterward, we're going to call the dispatch function to get something done, wrapping it with try and catch statement so the task won't break Jinx away. And after the task has finished its atomic function, we will proceed further into another scheduler, another time slice being scheduled. As far as the dispatch function goes, here you can see the location.hash is used as a big state machine. Each task can write different values. We have the idle, the start task. Every task can make up its own states and therefore can resume operation or dump itself the current operation to the hash and resume later on a different time slice. Imagine that we're going to transfer a file. We can divide the file into chunks and keep track about which chunk we're going to send next. Or we can use the offset and basically manipulate the range so we can know next time we will be activated which offset and forward we have to transmit to the server. We end up having enough generic code to have a framework. Now this framework is basically doing a couple of very interesting things. A, we get ourselves executed in the victim computer every X seconds. When we get executed, we have a try and catch statement that prevents any exceptions from bubbling and destroying the framework. And every state, every task has its own state and can simply resume operation from whatever state it's left before the scheduling is interrupted. Now, with this ability, we managed to pull two interesting things off. We can now queue tasks. We can now make a priority system to what's more important to the malware, transfer the file or attack a server. And we also can create the illusion of a multitasking. We actually have the ability to devote different time slices to different tasks and have the illusion that Jinx does multi-threaded approach. So for instance, you can launch a denial of service, upload a file to a server, and download a different file from the computer, all based on the time slice and different states mechanism. Our next step was basically to take Jinx from being a sophisticated malware, but static, into something more interactive, something which will be more prone to accept commands from us, to be more manageable, to have the ability to get new methods, new functions, and new targets in it. And we started to wonder how we can make Jinx such an interactive creature. Well, as you remember, when we spoke about the iframe and the same domain origin policy, we couldn't access information coming from an external server. We could only create the initial connection and transfer data over the URL. The solution to it was in fact quite late. All we had to do to get Jinx to be completely interactive is basically use the script HTML tag. The script HTML tag has the source attributes, which goes blindly, does not trigger or violating any same domain origin policy. Basically, what we have reached is a position where we have a virtual include statement. Each time we will refresh this statement, we'll be able to gain the opportunity to download some new data into Jinx. This data can be straight new code, new functions into Jinx. It can be new targets, can be new tests. We can manipulately upgrade Jinx from scratch without never touch base with the victim file system. Not once change the actual file on the victim file system, all thanks to the script tag. But before we came to understanding about how powerful the script tag really is, we actually started to dig further and lower to see what exactly has been included or supervised by the same domain origin policy. And to our surprise, we found some loopholes. Basically, what we found that through cascading style sheet link, it's possible to leak up to 15 different bytes through legacy properties in the DOM structure, which means we can now control 15 different bytes coming from an external server totally unrelated to us. Here you can see the elements which completely bypassing the same origin domain policy. Each element carries 3 bytes of length, and with that 15 bytes, what we can do? Well, it's a bit of a hardcore solution, but we really can preserve 5 bits for an opcode, let's say, and leave us the rest of the 13 bytes to be some sort of a payload. And with that, we have a mini scripting language which we can completely transfer and communicate over cascading style sheets. Now, taking into account the prototype and the data type of these values being an RGB, there is no right and wrong. Every value can be right. So we can include zeros, null bytes, high value bytes. Basically, it all goes all right, and there is no way to separate between it to another legitimate purpose of it. So far, what we have discussed about is that in theory, the ability to read files from the victim computer, smuggle them out, keeping the entire process stealth as possible, having a framework which can multiplex multi-different separate tasks at the same time, queuing tasks by priority, and allowing Mozilla to recover any possible memory consumption and CPU by keeping it low. What more we can ask from Jinx? Well, the future from Jinx is quite bright. We have 3 interesting suggestions which we can implement in Jinx, or you can implement them. Let's go over them real quick. We have the Google Ajax API feature, which basically through that we can eliminate the single point of failure of ET phone home static IPs or URLs. We can use Google Ajax API to basically search Google for our operator sites, which contains more instruction and more commands for us. We can basically exploit different URI handlers, or even inject a malicious URI handler during the setup and gain remote code execution from Jinx. Several URI handlers exploit has been published in the past, and they can be a good start. And of course, we have the favorite option of making people solve CAPTCHA for you. Now, it's quite interesting because if people, through fake pop-ups, will be getting to a situation where they will solve CAPTCHAs, they will allow massive botnets to perform brute force attack and other malicious activities on your favorite bank, e-store, and etc. If you want more information about the Chrome window and this entire environment which we got operated in, here's a good link from our friends at Mozilla. You can visit and check them out. It's quite educating. Okay, so far we have reached the first part of the talk. This was the design and the theory. Any questions? Okay, so here's Jonathan with the demo.